Welcome, everyone. I'm Ian Lindsay. I'm an archaeologist at Purdue University in Indiana, studying the Bronze Age in Armenia, as well as a current director and past president at ARISC. We're so delighted that you could join us for the second lecture in the 2021 ARISC Spring Lecture Series. In this series, we are highlighting the work of three early career postdoctoral scholars from the disciplines of geography, soil science, and history. In addition to today's talk, on April 16th, Dr. Ariel Etruva spoke on the borderization from the front lines, uncertainty and abandonment in the space between war and peace, which you can find on our website at www.arisc.org. And then on April 28th, 2021 at 12 p.m. Eastern, our own Amy Dobbs will speak on colonial governance, education reform, and the architecture of identity among 19th century Azerbaijani Muslims. And to register for that talk, also see our website, arisc.org. I now have the pleasure to introduce Dr. Scott Demyan, our speaker today. Dr. Demyan is an assistant professor of soil and environmental mineralogy in the School of Environment and Natural Resources at The Ohio State University. He holds a PhD in agricultural sciences from the University of Hohenheim, an MS in soil science, and a BS in environmental science from OSU. Dr. Demyan's research focuses on soil organic matter and its interactions with minerals under different land use systems, development of analytical methods for soil assessment, land degradation and soil health, and improvement of soil organic matter turnover and stabilization mechanisms in process-based models. He teaches courses on soil resource management, soil carbon, and environmental and natural resource management. Dr. Demyan is the chair of the Agricultural Soils Working Group of the Dr. Ratan Lal Carbon Management and Sequestration Center. He is a core faculty member of the Sustainability Institute and secretary of the Association of Ohio Pedologists. His initial introduction to the Caucasus region came during his work as environmental education volunteer for the U.S. Peace Corps in Armenia. So please join me in a round of virtual applause to welcome Dr. Demyan as ARISC's second presenter of the 2021 Spring Lecture Series. Take it away, Scott.
Yeah, thank you, Dr. Lindsay, for the nice introduction, and for ARISC for the introduction to talk today and the invitation. So yeah, thank you everybody for joining, and we'll start in today. So today I'm going to talk a bit about soils and ecosystem functions, and some of these are probably familiar to you, but some not so familiar, and then talk about some of the current pressures on our soil ecosystems, functioning and services, and then kind of into the main part of the talk, so infrared spectroscopy, what is it, and how can this be used to increase our knowledge on soil ecosystems and potentials in Armenia for rapid soil assessment. And so in the first section, so soils, I'm a soil scientist by training, so you're going to hear a bit about soils today. So soil ecosystem functions, if we look across the landscape, some of these become quite evident because they're related to above ground processes, but there's of course a lot of below ground processes going on. So we think about habitat for organisms, so not only above ground wildlife, but also below ground, nutrient cycling. So many plant available nutrients come from the weathering of geological material, parent material, but then also organic inputs and how they're utilized by microorganisms and made available for above ground plant growth. This is a big one here, of course, that we probably all think about, provision of food, of course. Most of our food is grown in soils, but then also fuel. We think about fuel wood, or also biofuels, fiber, if we have our cotton or wool clothes, also forage, food for animals, foundations for roads, our buildings, of course, homes. And some of the ones we might not think about so much. So soils are very important for water storage, water purification, and then also flood control. So depending on the type of land use that's in our watersheds. This will affect how fast rainfall then is it running off? Is it going directly into rivers and streams, or is it soaking in to the landscape? Climate regulation. So this is becoming more and more important with global climate change. So what is our current land use and how is that affecting the climate? And the last one here, a lot of my work focuses on carbon storage and sequestration in the soils and how we can better characterize soil organic matter. And if we look at the global carbon cycle, the amount of carbon stored in the top 1 meter of soils is greater than the carbon that's in the atmosphere. So depending on how we use the land and land use change, this will have a very large impact potentially on global carbon cycle. So just going a bit into introductory soils. So as soil scientists, we talk about soil forming factors and processes, and originally the main ones were biota, so vegetation and animals, parent material being basically what the soil is formed from, whether it's the bedrock in the place or glacial deposits, volcanic deposits, for example. Climate, so the long-term temperature and moisture regimes in an area. Relief, so is it a heavy sloping area? Is it at the bottom of the slope, top of a slope? And of course, time. So how long has the soil basically been exposed to surface conditions? So in the case of glacial soils, these are typically younger than older weathered residual soils, and these will all have effects on the soil properties and land use management. And in the past, typically humans were lumped into the effects of biota on soil, but increasingly, and geologists now consider that we're in the time of the Anthropocene, so humans are more and more being considered a soil forming factor in their own way, just due to the huge amounts of change that humans, so if you think about surface mining, for example, if you think about land use change through deforestation or overgrazing, things like that, the implant on the soils and the soil record is really immense. And so if we look at some of these degradation processes, the kind of universal thing about this is they're happening all over the world, and I'm going to show a series of kind of pictures and landscapes, some from close to my university where I work now, and then also from Armenia. But just to point out that these degradation processes are happening really everywhere. So if we think about agricultural land use, oftentimes some type of ground preparation is happening, whether that's plowing, some type of tillage or whatever. And oftentimes some of our best farmland is also located very close to waterways. So this is a small intermittent stream here. But you can see here the intensely plowed soil here would be prone to erosion, and due to the close vicinity here to the water, obvious connection to water quality. And if we look a bit more at agricultural land use, obviously oftentimes we harvest the grains, whether that's corn, soybean, wheat, here in the Midwest. If we think of rice and other things in other parts of the world, different cereal crops, whatever is left over from the harvest, sometimes it's burned in some cases, sometimes it's removed from the soil for other things, for example, for silage or for forage. In this upper picture here, you can see this is a field that has been harvested for forage, basically. So crop residue is very low at the surface. This is again prone to erosion, but you can see this picture here in the lower right. The crop residue has been returned to the surface, so this not only decreases erosion potential, but also adds organic matter, carbon, of course, but then also nutrients back into the soil. And you can see the effect, again, this is from near Ohio State University, you can see the effects quite obviously sometimes, and we'll get into a bit about soil color a little bit later on. But you can see here actually the effects of erosion going on here. So we have this kind of dark brown surface horizon, but you can see the subsoil. You can see the contrast in colors there is now at the surface. So this is a clear sign of erosion and active soil degradation going on. Most of the things that I've kind of highlighted are on-site impacts. So if you think about also compaction, this of course can lead to reduced plant growth, but then potential also off-site impacts. This here is a picture of Olentangy River, which runs through the Ohio State University campus. And you can actually see here, so this is the main river here, and this is a wetland that's kind of been constructed in the floodplain here. So you can see the water entering from this wetland is relatively clear in color, but you can see the brown color of the river here, which has, of course, soil from upland areas. So these lead to different issues, of course, of water quality, so eutrophication in our waterways, reduced fish habitat, and additional issues like that. And going back again to climate regulation and carbon storage, so you can see really the dramatic change in color here. So this is these are the same soil types. Actually, one's been under long-term crop use for many years, and this is an adjacent forest that excuse me, hasn't been cleared for agriculture. And you can immediately see the difference in color here is really dramatic. So looking at these kind of long legacies of land use change, they have a really profound effect on soil functioning and soil properties. And when we think about kind of dividing soil properties into inherent, so these are ones that are going to be relatively difficult to change, and then manageable soil properties, so ones that we can influence through our management. It's really important to know the effect of these different management techniques. So especially if we, in the case of Armenia, much of the land use is in open rangeland with some areas of forest. So looking at these contrasting land uses can actually be a good way to see kind of the range of manageable soil properties. So what would we expect, for example, soil organic carbon under long-term rangeland as compared to adjacent forests? Yeah, some further impressions of rangeland, and you can see here. So on the edge of the forest, the forest here has been is probably grazed to some extent. So this is reducing the regeneration, natural regeneration of these oaks. And so what is the impact that's having on, for example, carbon cycling and nutrient cycling? So there's quite a bit of things, especially on the side of manageable soil properties, but then also inherent soil properties. So for example, how much clay, sand, and silt is a site. This can give us inferences on soil fertility and also best management practices for our soil. But oftentimes the methods that we typically use, wet lab analysis, are relatively expensive. So one tool that we can potentially use is infrared spectroscopy. And in the few examples that I showed, especially the erosion example, we saw that there's obvious color differences and other differences that we can see from our very own eyes. And if we think of spectroscopy, this is just kind of an extension of that. And if we go back to fundamental physics, this has to do with the basically energy and wavelength. So if we look at the whole electromagnetic spectrum, we can see the small portion here that's actually visible light, so what the human eye can detect. And you can see that the infrared portion is approximately right here. And this nice little scale here kind of gives a depiction of what type of wavelengths we're talking about. So they're a bit longer wavelengths compared to visible light that we can see. And so what can infrared information tell us? So particularly in the infrared, and so I'll be focusing mainly on visible near infrared data, but this column here is also mid-infrared data, but this is information basically when different molecules vibrate. These have different transitions, molecular transitions, and depending on the elements involved in the molecule and also their coordination. So is it a chain? Is it bonding geometry at 90 degrees, for example, or 45 degrees? What other elements are associated with that? So these can be detected at specific wavelengths. And you can see here in the chart, these are just examples of different organic functional groups. Some important ones we can see are these aliphatic CH vibrations. These are carboxylates here. And so how do we acquire this infrared spectra? And if we think of the simplest level, our eye is very simple spectrometer. Obviously, we can't detect anything besides the visible wavelengths. And so infrared detectors can be proximal based. And so this would be, for example, a handheld unit or also in the laboratory. But spectrometers can also be on remote sensing platforms. So for example, satellite or space station missions, also based on airplanes or UAVs. But these are basically measuring similar wavelengths. So remote sensing offers the benefits of being able to cover large geographical areas. And depending on the return time, this can give you several pictures potentially during the season of an area. Of course, some issues with that: if the remote sensing satellite passes over and it's cloudy, for example, this will interfere with the obviously the visible, but then also the near and mid-infrared. So proximal sensing, so this would actually be either going out in the field with your sensor and measuring the soil there, or taking a sample from the field and measuring it back in the lab. This offers the benefit of less interference from atmospheric conditions and potentially higher resolution, spectral resolution. So if you just look at these two soil samples here, if you knew nothing else just besides the color, you can see this one's relatively light, this one's relatively darker. You can potentially hypothesize that this one here, due to its darker color, is higher in organic matter, which is giving it that darker color. And if one of these were redder than the other or maybe grayer, you can make some inferences for that. And so that's typically what we use infrared spectroscopy for, to make semi-quantitative or semi-qualitative determinations of different soil properties, and also in a quantitative form. So typically we always still need the traditional wet lab analyses. So these would be things like total organic carbon, pH, measuring soil texture, sand, silt, and clay, and using multivariate models to relate back to the infrared spectrum. Okay, so then that's a bit of background on infrared spectroscopy. So going into specific Armenia case studies. So why Armenia? Besides having beautiful landscapes and really diversity of land uses. So you can kind of think of it as a natural laboratory. So approximately the area of the US state of Maryland or Belgium. So in that small area, there's really a high diversity of biodiversity, and we'll also see, due to the elevation gradients, also climates. As the case in the South Caucasus, many of the areas are arid or semi-arid, and during quite a large part of the year, evapotranspiration is greater than precipitation. Many of these areas are potentially at risk for desertification. And it's been estimated the annual cost of land degradation is around 70 million. And furthermore, Armenia is a participant in the land degradation neutrality program. So this is a UN program, which I'll talk a bit about here in a minute. So this has the goal of increasing soil organic carbon content by 2.8% by 2040 from 2010 levels. And we'll talk a minute why this is important. And so looking at the land degradation neutrality framework, basically to achieve either neutrality or the kind of the final goal is to reverse degradation, so to improve land health and soil health. So starting out, you need to know kind of where you are at the beginning. So there's this baseline monitoring period, and then at future points, then additional assessment is done, and depending on if the metrics are increasing or decreasing, then this goal of degradation neutrality can be assessed. Now you might ask, how is this land degradation measured? So we can, especially from the soil standpoint, you can really measure a suite of different properties, particularly in this framework. It's looking at a couple of key things. So land cover as a proxy for land cover change, land productivity. This is kind of the health of the vegetation, and then carbon stocks meeting soil organic carbon. And as soil organic carbon is important for things like plant available nutrients, also overall soil health, soil important for soil microorganisms. This is kind of seen as a good general indicator of soil health. So how do we get the data for kind of this minimum data? 2 out of the 3 indicators, so land cover and land productivity, these can be estimated from both global land cover products from the shared database and net primary productivity. This can be relatively easily estimated using the normalized difference vegetation index, usually known as NDVI, or the enhanced vegetation index, also from remote sense data. Where the more difficulty comes in is the soil organic carbon stocks. So these should be estimated to 30 centimeters depth, and there have been some campaigns to estimate soil organic carbon stocks on a global level, which I'll show here in a moment. And so this land degradation is also related to, of course, the UN sustainability goals, particularly SDG 15.3. So by 2030, combat desertification, restore degraded land and soil, including land affected by desertification, droughts and floods, and strive to achieve a land degradation neutral world. So specifically going into the soil organic carbon estimates, which is kind of the most difficult part of this land degradation neutrality metrics, you kind of need 3 different components. So you need to measure soil organic carbon. So this is the actual elemental organic part of the elemental carbon of the soil. They have the guideline of 30 centimeters, 0 to 30 centimeters. Also need a measure of bulk density. So basically that's in a known volume of soil, how much solid or the mass of that volume. Especially in rocky soils, then we should also account for the percentage of that volume that's made up for rocks, because typically these don't store only very small amounts of carbon. And these measurements should be done at a baseline period and then approximately every 15 years. And so looking at the information available now, so in the context of Armenia and in several of the other countries, typically the Soviet Union had a very good soils program and also soil mapping. So in the case of Armenia, 1 to 100,000 scale maps were developed during the Soviet era. And these were similar in character, I would say, to, for example, what was going on in the US, in that these were basically object-based maps. So there would be different map units that would be based on pedogenic processes. So based on the position on the landscape and what type of rock the soil was formed from, we would expect to see that type of soil there. And so typically these map units would typically give a range of properties for that soil. And so these would be good for initial kind of reconnaissance information on the soil of an area, but not for small scale applications. And of course, these would be static maps. And going again, specifics of Armenia in the South Caucasus. So looking at the Kirpin-Geiger climate classification, you can see that there's really this huge variation in climate, which is strongly related to elevation. So kind of starting in the Ararat Valley here, we kind of have semi-arid to arid conditions, and then climbing in elevation. You can see here that there's a large portion of Armenia is kind of in this D classification. So this is cold, even though it isn't actually cold during the summer, but the mean annual temperature is considered cold. But some of these areas alternate with a dry or no dry season, and then warm, cold summer. And then also some actually areas that qualify as this E class, which is tundra up in the higher elevations. So we have the strong altitudinal gradients also regarding climate. And just to put this a bit in context for soils, so the typical, if we think of soils being divided into zonal, so a typical latitude associated with the soil, and azonal, which is more related to mountainous areas, we can see really the classic example. This is from the World Reference Base International Soil Reference and Information Center Soil Grids product. You can see the website there. With this color here, so this is Chernozem soil group. So this is the classic black soil. It's been called the royalty of soils. So these are really thick, dark soils, highly productive. And you can see it kind of starts out here in Hungary, but goes through Ukraine into across Russia here, and it really forms this zone here. And some of it drops into the northern Caucasus here, and it's a bit difficult to see here, but some of that actually extends down into Armenia, along with these other types of soils here. So if you actually go to this website and investigate some of the soils that are estimated from the soil map in Armenia, you can see that many of the areas, the probability of one soil type to another is pretty mixed, and that kind of goes with the way these new global maps were made. Basically, these were taken data points from around the world, but some areas, of course, are lacking in data points, the Caucasus being one. And if we look globally at these maps, the statistical models that were used to make these maps explain 30 to 70% of the variability of the reference samples used to make them. And so some areas have quite high uncertainty, especially in mountainous regions. Just going back here, this is a map of estimated soil organic carbon. So you can see in this map, it does pick up what we would expect to be this variation going from low elevation, kind of Ararat Valley, up into the highlands. This is approximately Aragats here. So as we go up in elevation, it gets cooler. Organic matter is decomposing more slowly. So we would expect that, but the uncertainty here is quite high. So this is where rapid soil assessment can come in. So kind of bridging what we have from these global estimates and going in between, bridging what we can measure in the lab, which is relatively slow throughput. So this project involved basically collecting soils from a couple of different target areas. So there's a countrywide soil sampling, and then two of the Mars or subregions, Armavir, which were relatively low elevation, warm temperatures, and Kotike Mars, which kind of span quite a large range in elevations, up to around 2,500, 2,800 meters, I believe, in Kajaran, which is a city far in the south. And so there was two parts of this: quantitative analysis using our reference methods, which include X-ray fluorescence, which was a total element analysis, and then also some prediction models that were developed actually using soils from Ohio, measuring organic carbon, clay, and pH. And separately, a qualitative analysis, so using the spectra themselves, interpreting based on soil color, and also looking at mineral abundance. So these different properties here, so organic carbon related to land degradation, but then also inherent soil properties, so clay and especially mineralogy. This is also important to deduce land capability, and then also soil forming processes. So some of the landscapes that were the range of landscapes, so you can see kind of semi-desert here, very short grass prairie, as it will, transitional forest areas, mountain steppe, and then meadow areas, the relatively higher elevation. And some of the different land uses here, you can see different forages planted. This is semi-natural high mountain meadow. Here you can see orchard interspersed with alfalfa here. And this is kind of, again, natural semi-arid vegetation. And some results here. So these are estimated clay contents. And one thing that we wanted to look at, what type of variation we could see between the region, because we would hypothesize that based on soil forming processes, that these regions would have different ranging characteristics. So this shows the range countrywide and estimated clay content. So going from near 0% up to 60%. And you can see the Armavir region being relatively higher in clay content compared to the countrywide average, and Kotike region being approximately the same, and Kadran being around 20-25%. So soil pH, so this is important for nutrient availability. So if the range in soil pH is very far away from circumneutral, say from about 6 to 6.8 is typically the optimum for nutrient availability. Very acid or very alkaline soils, you have potentially nutrient limitations. So you see countrywide median pH around 6. So we would, this is relatively, we would say relatively common, especially in this geographic setting, relatively low rainfall, so not extremely acidic conditions. Armavir, due to its lower elevation and probably presence of carbonates, so we would expect a higher pH there. And we did see some samples were relatively high, above pH of 8. And Kotike being higher elevation, there's generally higher rainfall there, and higher organic matter. You can see that pH is again around 6, and Kajaran a little bit lower than pH of 6. Okay, so thinking about our land degradation metrics, soil organic carbon. So this is estimated organic carbon, and countrywide an average of around 2.2. Armavir much lower, so around 1.5, which we would expect being in those warmer areas, semi-desert. Kotike region being in the cooler, semi-mountainous areas, higher soil organic carbon, so what we would expect. And then lastly, estimated soil organic carbon stock. So this would then be on tons per hectare basis, which is needed for the land degradation assessment. So countrywide, and this was based on an assumed depth of 0 to 20 centimeters with a bulk density of 1.1. So you can see that countrywide, a relatively high average, a little bit less than 50 tons per hectare. Low amounts in Armavir, again, that warmer, drier region, and higher in Kotike. And Kajaran is kind of intermediate between the two areas. So that was quantitative determination. So this next section is semi-quantitative, so looking at specific clay minerals, and this is really interesting, the visible near infrared, because often what we see in soils, they have a high proportion of quartz minerals, so silica oxide, silica dioxide, and in the mid-infrared, silica dioxide has strong absorptions, whereas in the visible near infrared, silica oxide does not have a vibration. So basically what we can see is the kind of underlying clay minerals, and also iron oxides and carbonates if they're present. So some of these are kind of giving us information on the underlying inherent soil properties that can give us information on soil formation. So hematite, we would expect this to be in high temperatures under well-drained soils. And you can see the estimated percent abundance is just relatively low across all the areas, so less than 1%. And generally, just looking at these soils, none of these were particularly red. So this is kind of what we would expect. Now, kaolinite is a common clay mineral, so it's a 1-to-1 clay mineral. It has a relatively low surface area and low activity, so it doesn't have much exchange capacity. And also nutrient holding capacity. So interestingly enough, Armavir had a relatively lower abundance, so a bit less than 15%, whereas Kotike had a bit higher. And this maybe indicates a higher degree of soil formation, diagenesis of kaolinite in Kotike compared to Armavir, or just different parent materials. It's a bit difficult to tell. Illite is a fixed 2-to-1 clay mineral, so it's very rich in potassium. You can see, especially Armavir, and actually also countrywide, there's a kind of a huge range in the variability here, so ranging from almost 0 up to 50%. And generally in Kotike, low proportion of illite. Smectite is a expandable 2-to-1 clay, so if you've ever heard of shrink swell clays, so these expand when they get wet and retract or shrink when they dry, and so areas that have a high proportion of smectite have this issue with shrinking and swelling, and so it does seem that generally there's kind of a medium proportion of smectite or smectite-like clay minerals present here. So you can kind of see the distribution countrywide, Armavir having slightly lower amounts compared to the Kotayk region. And carbonates, so carbonates would be related to pH. We would expect Armavir to have a higher proportion of carbonates. And from this estimation here, some of the soils have greater than 50% carbonates kind of in their mineral makeup. So potentially, and this is an issue when we measure soil organic carbon, one of the common methods to measure total carbon is by elemental analysis, which is basically heating the soil sample up to 800 or 1,000 degrees Celsius and measuring the evolved CO2. The issue is when we have organic and inorganic carbon, such as carbonates, then we have to take an extra step to either add acid to those samples to destroy the carbonates and then measure total carbon to take that as total organic carbon, or we have to do a separate determination for carbonates to subtract out. So this data here at least indicates, especially in Armavir, that there would be carbonates present there that we would have to take into account for that land degradation neutrality metrics of soil organic carbon. Yeah, so kind of just generalization in some of the areas. So Armavir, higher pH and presence of carbonates, generally lower soil organic carbon. Kotayk Mars having slightly higher clay content, Kajaran, higher kaolinite and smectite proportions. So does it seem realistic from a soil formation output? This does seem reasonable. So how do these methods compare to our traditional wet lab analyses? So one kind of benefit of infrared spectroscopy, whether it's lab or field-based, is that it's relatively rapid. The measurement takes usually just 1 or 2 minutes per sample. And if you've validated your methods, it can function as a high throughput, basically operation. So some of the different properties that I showed, so total organic carbon by elemental analysis, texture, so texture you would not just get clay content, but also sand and silt, pH and soil mineralogy. So these are some estimated costs per sample. So thinking about just one soil sample, if you wanted all this information by traditional methods, would be around $120, if not a bit more. And so if we're able to then create our prediction models with reference data for a smaller data set, and if the accuracy is that high enough, then we can apply it to unknown samples just with the infrared measurement. And just kind of in closing here, so I mentioned that some of the prediction models that we developed with data from Ohio were used to predict soils from Armenia, and you would think, well, why? That's probably not applicable because Armenia and Ohio have quite different soils and everything. And this is a depiction of the principal components, so the variability of the spectra. These are the Armenian samples, and these are the Ohio samples. So while the Ohio samples have slightly lower variability than the Armenian samples, it's surprisingly not that much. And we can actually flag the samples from the different data sets that don't overlap and would give lower uncertainty. So the kind of the beauty about the system is we can add in additional new samples to it to expand the prediction capabilities of it with new samples. Okay, I'll go ahead and wrap up there. So I'd like to thank the American Research Institute of the South Caucasus for support for field studies in the summer of 2019. And also I'd like to recognize the Center for Ecological and Noosphere Studies, National Academy of Sciences in Armenia, especially Professor Armen Sakatelian. So he he was my host for my summer stay in Armenia and put me in contact with his great research group at the Noosphere Studies. Fortunately, he passed away fall of 2019. I also like to recognize Dr. Gevorg Tipanosyan. He was my day-to-day counterpart and organized our field trips. And so go ahead and wrap up there, and thank you for your attention and welcome any questions.
Fantastic. Thanks very much, Scott, for that really interesting talk.